Hello everyone, welcome to the class. Just give me one moment, I'll check if I'm online. All right. Okay. Welcome. Hello everyone. Welcome back to the class. So in today's class, we are going to see we are going to learn some concepts from electric resistance and Ohm's law. All right. And let's begin. Before we go ahead, my name is Mohana. I'm a physics educator at Unacademy. So if you're taking class 11 and 12 physics with Unacademy, I'll be teaching. All right. And this is my Telegram group link. So if there's any update, I would be sharing those updates through this Telegram link. Right, so you can join me through the Telegram link, and also you can this is the common Unacademy, ICSE and ISC Board Telegram link. You can join here as well. Right, and just like how we have the YouTube classes, we also have special classes on the platform. So these special classes are absolutely free. You can take any of your favorite educators' free classes, right? And you can actually engage with the educators via the spool feature, and those classes are also live classes. So if you have any doubts, you can get them cleared then and there. And the link to the upcoming special classes are in the description box. You can click on class level special classes, right? It will take you to the it will take you to these particular courses, and you can click on the enroll. You can just click on the notify button, and when the classes go live, you will be notified. All right, Sanjit, good evening. And the upcoming special classes, these classes happen on the platform. So the continuation of today's class will happen in the platform tomorrow. All right, and then on 14th June at 4 p.m. we'll cover the concepts from magnetism, right? And on 18th June again we will be doing the current electricity topic on the Unacademy platform. Again, these classes are absolutely free, and the rest of the other classes that we'll be covering for this month is shared in the group as well. Okay, it's there in the link as well. All right, and even my Telegram channel will have all of these instructions. Now, in case if you're interested in the plus subscription, so these are the various advantages. One is you can learn from the comfort of your home, and also when you're taking a course with Unacademy, what you're getting, you're not taking in just one specific subject, you're getting 4 subjects, that is physics, chemistry, math and biology. You're getting unlimited access to 4 subjects. All right, and all the educators on the platform are good, so you'll be learning from the top educators. And every 4th session, right, every 4th session is a doubt clearing session. Right, so the first 3 days, whatever concept you're learning, the 4th class, you can, if you have any doubts regarding the concepts, you can ask. By any chance, if in case you couldn't attend one of the live classes, you can go through the class content, right? The class recordings will be available for you. You can watch the class recordings, come back to the class during the cloud class. If you have any doubts, you can ask, right? And we will be covering your entire syllabus. There is also the live test every other week. There would be live test series that are conducted. After the live test series, there will also be some analysis session. All right, then there is an ongoing batch right now for class 12. I'll give you the details by the end of the class. And normally with the plus subscription, if you take the longer duration, you take a course, you get the price per month goes down. Right, so if you take for 1 year, this is the price, that is 1,438 per month. Okay, but if you use my code, if you're using my code, you can use my code MT. In case if you're taking a plus subscription, you can use my code MTIS10. In that case, for the month that you're taking, right, per month, for this month, if this course is 1,438 per month, then you will get a 10% off, and you can buy the course for 1,229 per month. All right, now with that note, let's start. What is current electricity? We saw the concepts in the previous class. Just in case anyone who hadn't who did not watch the last class recordings, quick overview, right? If you're studying about these charges, if you study the properties of an electric charge that is in motion, okay? So if you study a charge in motion, what are the properties associated with a charge when it is in motion? It's called as, this is what you'll be literally studying under current electricity. You will be studying the properties of electric charges in motion. All right. Now, what is an electric current? Very simple concept. We saw this, right? If you have, let's say there is a wire, okay? Let's say there is electric charges, right, passing through this area. So we're going to take a very small cross section of this wire and we're going to see for a given time how many charges pass through it, right? So you get charge per time, right? Rate of flow of charge per time. That's nothing but your electric current. Okay, so these concepts we saw yesterday, right? So for electric current is given by electric charge by time, right? Electric current is given by charge per time, and from here you can say that from here you can say current I is equal to Q by T. Anybody can give me what is the unit of electric current? What is the unit of electric current? What will be the unit of electric current? This is basically coulomb per second, right? Coulomb per second, and electric current is given as amperes. All right. So there are two types. Electric current is given as amperes. That's right, Sanjit. It is basically 1 ampere. 1 ampere is nothing but if 1 coulomb of charge is flowing in per a particular given unit area per second, right? So 1 ampere will be coulomb per second, right? Coulomb per second is 1 ampere. 1 ampere is 1 coulomb per second, right? That's electric current. Now, electric current, in electric current you have two types. One is transient current. If a current happened for a short duration, we saw an example in the last class. What is an example of a transient current? Example of transient current, anything you can think of. Lightning is an example of transient current. Likewise, we have another one as steady current. Okay, steady current is the charges flow in a steady manner. The one you get in your transistor radio, the one you have in the touches, the battery you're using there, all of these work under steady current. Okay, then electric current SI unit is ampere, and 1 coulomb of charge, if it crosses an area of 1 second, then the electric current through it is called as 1 ampere. Right? We also saw this. Now, there are two currents, right? We normally talk about a conventional current and electronic current. Okay, conventional current, that is in any circuit that you're taking, the direction of the positive charge is taken as conventional current, right? For example, let's say there is a resistor and across it, let's say you're connecting it across a battery. For example, right? This is the positive terminal, negative terminal. So the direction of the conventional current is always from positive to negative terminal. All right, but electronic current is always in the direction opposite to this conventional current. So if conventional current is in this direction, then the electronic current in the circuit will be in the opposite direction. Electronic current just talks about the flow of electrons, in which direction the electrons are going, right? They are going from the negative towards the positive charge. So they are going from the negative to the positive charge. So they are opposite to the conventional current. So conventional current direction is in the direction opposite to the electronic current. I'm going very fast because we covered all of this in yesterday's class. All right. Now, what quantity is electric current? Is it a scalar quantity or a vector quantity? Electric current, is it a scalar quantity or a vector quantity? Okay. So electric current, it has both direction and magnitude, right? Okay, Sanjit, electric current has both direction and magnitude. Okay, for example, let's say there is a 3 amperes of current coming in this way, right, in one wire, and in another wire another 4 amperes of current is coming. So it has direction and magnitude, right? So if it has a magnitude, that is, it has 3 amps and 4 amps, magnitude is given, it has a direction. We are giving a specific direction also, right? So if this is the case, then you should be able to apply laws of vector addition. So then it should obey vector addition, okay, the laws of vector addition. But experimentally, when you observe, okay, when you measure this current, okay, experimentally, if you're measuring this current over here, right, right? What you will be getting is that you will get a 3 amperes plus 4 amperes. If in your meter, it will actually read 7 amperes of current is flowing, which means this electric current over here, right? Though it has both magnitude and direction, it is not following vector laws of addition, but you can add them using the ordinary common algebra. Okay, so though the electric current has both magnitude and direction, because they do not follow the laws of vector addition, they are not vector quantities, they are just scalar quantity. Clear? Okay. Now, from there we learnt about what is Ohm's law, right? So George Simon Ohms, in the year 1928, he did he actually got an experimental observation. All right. So what he did, he connected a resistor, right? He had a resistor, he connected it across a battery, right? And he connected a voltmeter across this particular resistor R, right? And let's even have a, right, let's say there is also a key. Let's say there is the circuit, right? Let's say there is a key, and also he connected a ammeter in series, right? Now, what he observed was this: the current flows in this direction, right? When the circuit is closed, the current flows from the positive to the negative terminal of the battery. So when that happened, he actually saw as the current increases, right, what is the voltage, right? As the current increases, he took the relationship between current and voltage. He just made a graph between current and voltage. And what he saw was that as and that particular relation he gave between the current and potential difference, right, is known as the Ohm's law. Okay, and what was observed was that as the current increased, right, as he increased the current value of current, okay, current has even 1 amperes, let's say 0.5 amp, 1 amp to 1.5 or some value, right? As the current increased, as the voltage increased, right, as he increased the voltage, he saw that there was an increase in current as well. Okay, so the current flowing through a the current flowing through a conductor is directly proportional. Okay, it's directly proportional to the potential difference applied across its ends, right? As he increased the potential difference from 1 volts, 2 volts, 3 volts, 4 volts, he tried to measure what is the current happening, okay? But this the potential difference is proportional to current provided the temperature and any other physical quantities remained unchanged. Okay, temperature changed, then there will be a change in current for a given potential difference as well. Okay, now potential difference, he found potential difference is proportional to the current, because when you plot a graph between voltage in the x-axis and current in the y-axis, you get a straight line graph. Okay, now so to remove the proportionality constant, he introduced R. Okay, this R is called the resistance of a conductor. Okay, now the slope of this graph will basically give you the resistance value. Now right now the resistance of a conductor is nothing but it is the property of virtue by which it opposes the flow of charges through it. Okay, so if a conductor has more resistance, then less current will flow through it for a given potential difference. Okay, you keep the potential difference the same, increase the resistance value, right? Then you can see current flows less, right? If you reduce the resistance value, current flow will increase. Okay, so from here, from this relationship V is equal to IR, which is basically your Ohm's law, right? Which gives the equation of the Ohm's law. From there you can say the resistance is equal to the ratio of potential difference applied across the conductor to the current flowing through it. Right, that gives you the resistance value. I'm going a bit fast because these concepts we have covered in the previous class as well. So what is the SI unit of resistance? You would have done this in your previous classes, in your lower grades as well, right? In 10th grade, 9th grade, you would have come across this. What is the SI unit of resistance? SI unit of resistance. The SI unit of resistance is ohms. Okay, so for example, if let's say, okay, 1 ohm. Okay, how do you define 1 ohm? It's very simple. Let's say resistance of the conductor is said to be 1 ohm. If a current of 1 ampere, right, flows through it on applying a potential voltage of 1 volt. across its ends. Okay, when you take a particular any conductor, right? Any conductor, you can take any conductor, any material that have some sort of resistance is called as a resistor, right? So if you take any conductor, okay, or resistor, and if you apply some potential difference across it, which means you're connecting it across to a battery. Okay, let's say this is the battery. If you're connecting it across to the battery, there will be a potential difference that is developed across its ends, right? Now this potential difference would be 1 volt. Okay, if you apply the potential difference of 1 volt, okay, because of it, if 1 ampere of current is flowing through, then the resistance of this of this conductor would be 1 ohm. Okay, so that is the definition for 1 ohm. So from here you can say this 1 ohm, we use the Greek symbol, this symbol, right? 1 ohm is equal to 1 volt ampere inverse 1. Now any material that has some resistance is called as a resistor, right? Sanjit, ohm is correct. Now what are the factors? Now we usually in last class also we saw that the symbol for resistance is this one, right? If you use this symbol, it means it's a fixed value. This could be 2 ohms or it could be 5 ohms. Now if you use this symbol with the variable symbol, which means this is a variable resistor, in this case you can change the resistor value. Okay, so these are the symbols that we actually saw in the last class as well. Now what are the factors? What are the factors affecting the resistors? Okay, now at a constant temperature, the resistor of a conductor depends on few factors. Can you name some of the factors that the factors affecting the resistance? What is resistance dependent upon? Okay, the resistance depends upon the length. Okay, the resistance of the conductor is directly proportional to the length of the conductor. Okay, so R is proportional to the length L. Okay, now if you take that's right, Sanjit. Second is area of cross section or the thickness of the conductor and the nature of the conductor, right? Right. So in case if you increase, if when you compare if this is the length of the conductor, right? If you increase the length of the conductor, then the resistance also increases. And as mentioned, that is right. The next one is basically your area of cross section. Now resistance, in this case, resistance is basically inversely proportional to the area of cross section. We saw the example, right? If the area is too small, then the resistance is basically more. If the area of cross section of the conductor is more, then the resistance drops, right? The resistance becomes less. Next, the third thing is basically your nature of the material, right? The nature of the material, it depends on what material it's made up of. If you take the same length, same cross-sectional area, now if you take a nichrome wire, right, its resistance is 60 times more when you compare it with a copper wire which has the same length, same cross-sectional area. Alright, now from here we can say resistance, right, is proportional to length of the conductor and area of cross section. To remove the proportionality constant, we introduce this alphabet, right, rho, which is the proportionality constant, and this is basically called as your resistivity. Right, now resistivity, or sometimes we call it as the specific resistance as well. Alright, now from here we can say that what is resistivity or specific resistance? Very simple. From here actually we can get in case if you make the length, okay, if R is equal to what, rho L by A, okay, if you take if you make the length as 1 unit, okay, and as well the area of cross section to be 1 unit, right, then what happened to R? R will be equal to rho. Okay, so now you can define specific resistance or resistivity, right, of a material may be defined as the resistance of a conductor of the material having unit length, right, having unit length and unit cross sectional area. Okay, now what will be the SI unit of resistance? It's very simple to find, right? So SI unit, so over here, from here we can find rho will be equal to R into A by L. right? So if you want the SI unit of rho means this is basically ohm, resistance is given by ohm, area is given by meter square, right, by length is given by meter. From here the SI unit will be equal to ohm meter. From here you get the SI unit as ohm meter. Okay, ohm meter is the SI unit of resistivity. Alright, so till this we would have done in the previous class. So this was a quick overview for those of you who hasn't attended the class. Now let's see what is current density. Okay, current density is a very simple concept, right? Now you take a particular area. Okay, let's say there is a charge flow over there. Okay, if a charge is flowing in a particular area, what happens? There will be a current, right? If charges are flowing, what happens? There will be, right, let me just quickly get, right, if there is a charge flow, then there will be then there is basically current, right, flowing through the, then there's a current flow, right? Now we are going to introduce, right? Now there's a current flow. Now the current density at any point inside a conductor is the amount, okay, it's defined as the amount of charge flow per second through an unit area held perpendicular to the direction of the flow of charge at that point. Okay, now there is a charge flow, and for a particular area how much charge is flowing per time for a given time gives you basically what? Gives you basically the information about current I. Alright, flow of charge per time gives you current I, right? Now if you introduce an area over there, okay, if you introduce an area over here, and over here we want to find out how many, okay, how many charges are passing that particular area, right? If you want to do that, then let's just give me 1 second. Right, so right, how many charges are passing through this particular area, right? Now current is in this direction. Normally when you have area, we introduce a concept called as area vector, right? How do we find area vector? Area is actually all right, okay, so area is basically is a scalar quantity, right, when you're talking about area. But how do you make it a vector, right? We introduce a quantity perpendicular to it and we give it a direction, right? So if this is my area, perpendicular to that will be my area vector. This is my area, perpendicular to this will be my, if this is my area, perpendicular to this will be my area vector, right? So if my area is over here, then perpendicular to this, which is basically perpendicular to this particular surface that is over here, which is basically this side, right? This will be my area vector, right? Let's say this area vector is given by A. Okay, this is for the given area. Okay. All right, so from here we can say this basically is area, right, area A. Now this is your area vector. Now that it's given a direction, you can say like it's moving in this direction, right? So this is an area vector. Now how many charges are crossing through that area vector, right? That gives you your current density, right? And it's a vector quantity, right? So here you can say area vector is given by J, right? Area vector, this is basically given by current density is given by J, and this J is given by how much amount of charge is flowing per second. Okay, how much amount of charge flow per second, that is Q by T for the given area, right? For the given area through a unit area held normal to the direction of the flow of charge. Okay, so its rate of flow of charge per second gives you what? Current by area. This is the area vector. Now all the time, if you look at the, if you basically look over here, you can see that the direction of this current vector, right, the J, in this case current density, it's a vector quantity. The direction of it is given by the direction of the positive charge, right, the direction of the flow of charge, right? So if this is the direction of the flow of charge over here is giving you current, right? Whatever is the direction of current density will be in that direction, right? But all the time the angle in this case between the current density and the area vector is basically 0, right? But in this case, right, not all, but in some time, right, in some cases, the direction of your right, your this might be the direction of the current, right? This could be the direction of the current, and your area vector might form an angle with this way, right? It may not be perpendicular to the current flow, right? Now if you draw an area, right now if you draw an area this way, right, now these are the electric field lines passing through, and if this is the area, then if you draw a perpendicular for this area, right, earlier this was your area, right, now the area has gone this way, right, there is an angle. Right now, this is my normal, right? This is my area vector, right? This will give you your area vector. Now, with the current, with the current flow, right? This makes an angle theta, right? Now, same concept as we did in case of electric flux, right? We did electric flux, so it's in this case, right? This will be an, right? If you're taking a vector towards it. Now, in this case, you can give area vector can be given as what? J is nothing but I by A. But what is A over here? A over here is nothing but, because we saw that the area vector, right, will be in the direction of the current electric field, right? So in that case, this A over here will be what? It will be AN, this angle into cos theta, right? So here you can give this component AN, right? This, which is in the direction of the current, is nothing but A into cos theta. Alright, so as the angle changes, right, see, if so many field lines were initially there, right, now how much ever field lines were flowing earlier, as this angle, right, as it tilts, see, the number of charges flowing per that area also decreases, right? And here you can give the current density, right? You can give this current density, right, in this case, whatever we were doing here, right? J is equal to, in this case you can say, from here we can say I is equal to J A cos theta. We are just giving from here, this is equal to, I is equal to A J A cos theta, right? And in this case, you can, current is basically, in this case you can give this as a vector quantity, right? J is a, this is a vector quantity, right? You can give J as, this as J vector cos theta, so it will be a dot product into A vector, right? So current density is a vector quantity, and its direction will be in the direction of the positive charge, the direction of the charges in which it is moving, right? For a given area, how much charges is flowing for time was basically, we use that concept to derive what is the current density, no? Now, what direction the charges are moving in, that gives you the direction of the current. No, whatever the direction of the current, that will be the direction of your current density. Alright, so here it is a vector quantity, and we have written current density, right, in terms of your vector equation as well, right? Okay, from here we can say, from here if you see this current being a scalar quantity, right, now this is expressed as a product of two vector quantities. Alright, and what will be the unit? What will be the unit of current density? The unit of current density, in this case, the unit of current density will be ampere per, right? Current density is given by J is equal to I by A, right? This is ampere, and the unit of area will be meter square. So J is basically ampere, meter square is the SI unit of J. That is, current density is ampere meter square. Okay, so if you want to give the dimensional formula of current density, that will be, this will be ampere, meter square is given as AL, right? This is the dimensional formula. Okay, so this is about current density. If you have any questions, ask me now, otherwise I'll go ahead. Right, so let's learn about few more quantities. Right, what is conductance? Okay, now the The conductance of a conductor is very simple, right? It's basically conductance is opposite of resistance. Resistance, what it does, it opposes the flow of current. So conductance means it allows the conductance of a conductor is nothing but the ease with which the electric charges flow through it. That is given by conductance. Okay. Now conductance is basically, this is equal to the reciprocal of resistivity, and usually we can give conductance by this symbol G is equal to 1 by R. Okay, so conductance is if you're writing conductance is basically 1 by resistance. Okay, so what will be the unit of conductance, right? So we give conductance by the letter G, right? So if you're looking at the unit of conductance, now that would be, in this case it will be 1 by, this will be, in this case it will be 1 by ohm, right? 1 by ohm. Right, so you can give it as ohm inverse, right? Sorry, we don't write we actually don't write it as ohm inverse, right? We have to write down the whole cent name, right? This in case we write it as ohm inverse, right? Or we give mho, or we also give one more unit, Siemens, okay, which is given by capital S. All right, all these are the unit of conductance. Now, similar to this, we have what is conductivity, right? Now, the reciprocal of resistivity. The reciprocal of resistance is conductance. So, reciprocal of resistivity of a material is conductivity. Okay. Now, conductivity is given by this symbol sigma rho. Okay. And this is equal to 1 by rho. This is conductivity. Will be equal to 1 by resistivity. Right. So what will be the unit in this case? Resistivity unit is given by 1 by, in this case resistivity unit is ohm meter, right? Ohm meter. So conductivity unit will be mho meter, right? It will either be mho meter, or you can give it as ohm inverse 1, meter inverse 1, right? Or you can give it as Siemens per meter. These are all units of conductivity. Different ways you can write conductivity. Okay. Next is, let's see what is the vector form. What is the vector form of Ohm's law? All right. Right. So here, let's take E. Let's take E to be the magnitude of your electric field. Let E be the magnitude of electric field. Okay. Let this be the magnitude of the electric field in a conductor. Okay. And let's say the conductor has a length L. L is the length of the conductor. Okay. Then let's say a potential difference is applied across the length, right? There is a particular conductor, right? It is placed in the electric field. So the magnitude of the electric field of this produced by this conductor, right, is basically E. Then we are giving the length of the conductor, and if you are actually applying a potential difference, meaning if you're if you're connecting it across a battery, right? You're connecting this across if you're connecting this conductor across a battery, right? Then you're applying a potential difference across this. Right, let's say this potential that you're applying is given by V. Okay, this V gives you the potential difference. Potential difference developed across this particular conductor, across the ends of this conductor. Okay, that's given by V. A potential difference. Right, this is the potential difference developed across its ends. Okay, then from here we can say, right, V is equal to E into L. Okay, your potential difference. This is a relation connecting potential difference, electric field, and the length. Okay, so this you will actually derive this equation in your electrostatic unit. All right. Now from Ohm's law, right? This is one part, right? From another part we know Ohm's law. From using Ohm's law we know V is equal to what? From Ohm's law, V is equal to IR, right? R, we just derived for R, right? R can be given as rho L by A, right? Now we have two equations and let's try equating them, right? Let's try equating them. Okay. Now this is EL, right, is basically equal to I rho L by A, right? So from here, we L and L, this gets cancelled. So you'll have E is equal to I by A into rho, right? What is current per area? What would be current per area? Current per area is basically given as E is equal to current per area is basically given as right? Current per area is basically given as current density, right? J into rho, right? So this is current density, which is current per area, right? Current density per rho, right? Now, as the direction of current density, right? This is current density is a vector quantity, right? Now, the current density's direction is the same as the electric field direction, because electric field is again a vector quantity, right? So we can write this equation in its vector form, that E vector is equal to J vector dot rho, right? Now, if you want to write, if you take the reciprocal of the same, right, then you can write, let's say J vector is equal to 1 by rho into E vector. Now 1 by rho, 1 by resistivity is nothing but conductivity, right? Now this forms, these two equations that you're seeing over here forms the Nick, you are in 9th. Yes, Nick, if you can follow what yes, you are welcome to stay in the class, Nick. You can actually, this is a class 12 topic, but I'm just doing the basics. So you can actually continue. If you have any doubts, you can ask me. I'm happy to explain. All right. So this is basically given by electric field, and this is basically this equation, that E is equal to J into rho, and this and J, right? Current density is equal to rho into E. So this forms the vector equivalent of your Ohm's law, that is V is equal to I into R. Okay. This forms the vector equation of the Ohm's law. Right. Now, from here, let's learn about the classification of materials based on resistivity. Right. So, based on resistivity, right, you can actually classify materials into three types. One is, it is a conductor. Okay. The materials which conduct electric current fairly well are called as conductors. Okay. So here these materials, right, since they conduct electricity fairly well, which means the opposition they offer to the electric current is low, which means their resistance is low. Okay. Their resistance sometimes is in the range of 10 to the power of -8 ohm meter to that of 10 to the power of -6. This is the range ohm meter. Okay. Copper and aluminium, these are some of very good conductors because they have very low resistivity. Okay. And nichrome has a if you see, nichrome has a very high resistivity, right? So based on it, nichrome is not a very good conductor. All right. Normally when you see an electric iron or an electric heater, these actually make use of a good conductor, right? These are examples of good conductor. They make use of, they are made of materials which are very good conductors, right? Next, the other type are basically insulators. The materials which do not conduct electric current are called as insulator, which means they have a very high resistivity, right? So in this case, they have, in the conductors, if we are saying the resistance range is -8 ohm meter to 10 to the power of -6 ohm meter, right? In case of insulator, their resistance will be too high, right? This is a very low resistance, but in case of insulators, the resistor will be 10 to the power of 4 ohm meter. Okay. Now, example of insulators, if you know any good examples of insulators, you can share it in the chat box, right? Example of insulators is mica, glass, rubber. All of these are very good wood. All of these are very good examples of insulators, right? So insulators, they are usually used to block electricity, right? Because they have high resistivity. Next, the next one is semiconductors. Now these are materials whose resistivity lie between those of the conductors and insulators. Okay, so these resistivity lies between 10 to the power of -6 ohm meter to that of 10 to the power of 4 ohm meter. Okay, they lie between this range. Okay, example of semiconductors: germanium, silicon. These are some types of, these are the typical semiconductors. All right, now semiconductors you will be learning in your chapter, in your semester 2. You will be learning more about semiconductors, but in this class, in the classes that is happening about in the platform, Unacademy platform, there are few classes happening for current electricity. Like in those classes, I'll try to cover some of your some aspects of semiconductors. All right, this is the classification of material based on semiconductors. Right, now what are there are some common commercial resistors. All right, there are actually two types of common commercial resistor. One is a wire bound resistor and a carbon resistor. Okay, the wire bound resistors, these are made of windings of wire of an alloy like magnum, right, constant, and also nichrome, or on an, they take an insulating base. On that, these wires made of these material, right, something like made of nichrome, right, it's an alloy, right. These wires are wound on that particular insulating base. Okay, then the advantages of using these alloys is that they are relatively insensitive to temperature. Okay, because when you're learning about the voltage to current relationship, right, when you're learning about Ohm's law, this is for a given constant temperature, right. If temperature changes, the value of V and I also changes, right. So because of this, the advantage of using these wire bound resistors is that they are relatively insensitive to temperature. But one of the inconvenience is that a large length is required if you want to make a resistance with high value, right. If you want to increase the resistance, right, what are the ways in which you can increase the resistance? If you want to increase the resistance is proportional to L, right. R is proportional to L. So if you want to increase the resistance, you have to increase the length of the wire, right. So in this case, to get a very high resistance, you have to take a very large length of wire. So that is one of the disadvantages or inconvenience. Okay, next type is the carbon resistors. All right, these are made from a mixture of carbon, black clay and resin blinders, which are pressed and then molded into cylindrical rod, okay, by heating process. Now these rods are again enclosed into ceramics or plastic jackets, and the carbon resistors, right, these are widely used in electronic circuits of radio receivers and amplifiers, right. The one you would have mostly come across in your labs would have been a carbon resistor. Okay, there are some advantages for these carbon resistors. One is they are made with resistance, right, value ranging from a few ohms to several million ohms. Okay, this is one advantage. They are quite cheap, and they are also very small in size. They are compact. Okay, and and also they are very good enough for many purposes. They're very good enough. They're also very good for many purposes. Okay, now if you see a resistor, right, usually all of the resistors will be color coded. Okay, we don't use numbers, but we use color codes. Why? Because in case if you're using numbers during transportation or anything, if the ink or the numbers, right, which is written on, right, got erased, then you might think, okay, let's say the value of this is around let's say the resistor value is 9. For example, if part of the value gets erased and all you see is 0, or all you're seeing is just part of the value, right, then what happens, this might actually, let's say, okay, for example, let's say the value of the resistor is 18. Okay, now let's say while transportation, one part of the value is gone and you're just seeing 1. You might think it is just an 1 ohm resistor, right, but it's actually 18 ohms. So this will not make it feasible to use it in any circuits, right, in electronic circuits. Now this becomes quite dangerous, right. Because of it, we follow a color code for carbon resistors, right. So if you take a carbon resistor, right, if you basically take in a carbon resistor, this will be color coded. Okay, they will usually be 4 bands of colors. Okay, and they'll usually be like around 1, right, usually you see 4 different bands of colors, and these colors actually represents what is the value of this carbon resistor, right. You will actually see 4 different bands, of colors, and using those 4 different bands of colors you can actually see, learn what is the value of the resistor. Okay, now so the color code of carbon resistors, we usually follow these list of colors, right? They start from black, brown, red. So black, again the letter A that goes with black is B, then you have brown, so this is B again, and then you have red, so R, orange O, yellow is Y, and green is G, and blue is V, and right, violet is V, and then you have gray, which is G, and white, which is W. Okay, this is the letter 8 that goes with it. So each color represents a particular number. Okay, so if it is black, it means the number that goes with it is 0, for brown 1, and red 2, and so on. Okay, each of these letters goes ahead with a particular number. Okay, and there is actually a multiplying factor also. Now for the multiplying factors, when you see actually black, the multiplying factor in this case will be 10 to the power of 0, and then you have 10 to the power of 1, 10 to the power of 2, right? And for orange you have 10 to the power of 3, 10 to the power of 4, 10 power 5, right? 10 power 6, 10 power 7, 10 to the power of 8, and 10 to the power of 9. Okay, and there might be 3 bands, right? And one of the bands would have this color, either it will be gold, silver, or no band, no 4th band. Okay, now these color bands that you're seeing on the resistor, these normally talk about the tolerance level of a resistor. Okay, now there are 2 system of markings for this particular resistors, right? One is, we're almost going towards the end of the class, so what I'll do is I'll give a quick overview in this class, and in the upcoming classes I'll we'll look into more of the color codes of carbon resistors. All right, so for example, let's say in this case, let's say, okay, you have a resistor. Let's say you have a resistor, okay, and the resistor might have 3 bands on it. So the resistor will usually have 4 bands on it, right? So usually, let's say you have, okay. You might see 1, 2, 3, and the 4th one could be a silver or a gold color. Okay, so these corresponds to, it might be may not be the same color, it might be different colors as well, right? These corresponds to a different thing. Okay, this first band gives you your first significant digit. This gives you your first significant digit. Okay, so seeing the color, if this is red, okay, then you go to this column and you have to see what is red. Red, the first number that you're seeing, right, that is 2, right? That will be the first significant digit over here, 2. Now the second band over here, this actually gives you your second significant figure. Okay, this indicates, the second band indicates your second significant, second significant figure. All right, so the second significant figure in this case, this would be, in this case you have to right, this again you have to go, this is again, if you see red is again 2, right? We have taken red, so again this will be 2. Okay, now the third band that you're seeing over here, right, the third band usually talks about third band actually talks about your decimal multiplier. What is the decimal multiplier? Right, the decimal multiplier in this case, because we got what, red, right? So the decimal multiplier in this case, right, this is also, in this case we got a red color, right? Again here it is another red. Now the decimal multiplier is also red, right? Then the decimal multiplier is this third column, the multiplier column you're seeing. For red it is 10 to the power of 2, right? So this will be 22 into 10 to the power of 2, okay, ohm. Now the fourth band, it can be there, it can be a gold band or a silver band, or right, so this third or it could be, there could be no band as well. Okay, the fourth band just increase, it talks about the tolerance, okay, or the possible variation in percentage of the indicated value, whatever the value over here is, right? It talks about the tolerance, right? It talks about either the tolerance or the variation in percentage, then that is given over here. Okay, now if the fourth band, in this case there is no band over here, if the fourth band is absent, means it means the tolerance will imply this is basically plus or minus 10-20%. If there is no band, then the tolerance level will be plus or minus 20%. Okay, so this is the value of the resistor. R is equal to 22. R is equal to 22 into 10 to the power of 2, right? Ohms, and this value could be off by 10, could be plus 20% off or minus 20% off. That talks about your tolerance level of this particular resistor. Okay, now how do we remember the color code? To remember the color code, there is a very simple thing you can use. You can use this thing, B.B. Roy of Great Britain had visited Great Way of India. That is one easy way to remember. And in the first case, this first B represents your black, so the significant figure is 0. Then this is brown, this is basically 1, right? And then R is red 2, orange will be, then O is orange will be 3, yellow 4, right? In this case, G is basically green, right? Green is 5. Then again you have another B, which is basically blue, 6, right? And V is violet, 7. Again you have G, which is gray, this is 8, and white is actually 9. Right? So the color code is used to indicate the resistance value of a carbon resistor and its percentage accuracy. Okay, so this is the color code for your carbon resistors. And with this note, let's try finding the value of one other resistor, right? So let's say we have a resistor. Let's say this is a resistor, and let's say there is, let's take with different bands. Okay, let's say it has a yellow band. Let's say this one has, one second, right, let's say this one has a yellow band, right? First band is yellow, followed by, let's say it has a violet band, right? Then followed by, let's say there is right, let's say there is a green band. Okay, and I am just going to give this band, right? I'm going to just give 3 bands. Okay, now what will be the value of this resistor? Very simple to find, right? The value of this yellow band, right? What is the value? That gives you the first significant digit, right? So LO over here is given by LO, right? Is what LO is given by the value 4, right? So this is 4 into, right? The next one will be, the resistor value will be, the resistor value in this case will be 4. And what is violet? Violet is given by 7, right? Into this third band gives you the multiplier, right? The third band, significant figure, right? The third band will always indicates the power of 10 with which these 2 digits has to be multiplied. Okay, so this green over here indicates 10 to the power 5, right? Into 10 to the power of 5 ohms. If there is no bands, then it will be equal to plus or minus 20%, right? If there's no band, fourth band present, that is your tolerance level, meaning this 47 into 10 to the power of 5 ohms, this band value is there, no? So this could be more 20%, it could be 20% more than this value or 20% less than this value. That is the resistor value. Okay, in case if it was silver coated, then the tolerance level will be 10%. Okay, in case if it was gold coated, okay, now this makes the accuracy very good, right? Then the accuracy of this particular resistor is just off by 5%, or the tolerance is just 5%. Okay, so this is one system of bands. Okay, there is another kind of resistor which actually makes use, this is the second, there is a second system of resistor. So what that resistor says is, it basically has, okay, in the second system of resistor, right, you will have to, this basically gives you the end, right? You basically have the end, right? And they might be there might be a ring over here. Somewhere over here there might be a ring, and they would have provided a dot. Okay, the color of the ends, there are two sides over here, right? In the ends, in these two sides, the color on these two ends, this is another type of resistor, right? This is the second system of resistor. The color on the ends, right, those basically gives you the significant, okay, gives you the color of the body. What is the color of this? Is it red, white, right? If in case that, if this color is basically yellow, if this is green, okay, this whole body is made of this green color, right? Then that gives you this color gives you the first the significant digit. Okay, this is the color of the body, but this gives you the first significant digit. Now what is the color of the ends? That gives you the second significant digit. Okay, and whatever is the color of the dot over here, this will give you the number of zeros, that is the multiplier value we saw, right? What was the multiplier value? This will give you the multiplier value. Okay, this gives you gives the number of zeros to be placed after the significant figures. After these two significant figures, the color of the body is the first significant figure, color of the ends is the second significant figure, the multiplier, this is how many zeros you need to multiply with. Okay, and the ring color, the ring, this is basically the ring. Okay, and the ring talks about the tolerance or the percentage accuracy of this value of this resistor. Okay, this gives you the tolerance value. This is another type of resistor. Okay, more about this resistor we will see in the upcoming classes, and tomorrow there is a class happening for electric current around 4 p.m. on the Unacademy platform. That is an absolutely free class, so you can just click on the link in the description box and you can actually enroll for that particular class, right? And in tomorrow's class we will be learning about drift velocity, and we will try to learn about some relationship between, right, your drift velocity and current, and some derivation we would be doing in the class on the platform. Okay, right. So the continuation of today's class will happen on the tomorrow's free class on the platform. All right, the class will be at 4 p.m. Now, if in case you are interested in the taking a course with Unacademy, then you can actually register for this course. This is actually an ongoing course. This is an ongoing plus course which started on June 1st, right? The mode of delivery will be in English. So for physics, I would be taking math, Jyoti ma'am will take, Manisha ma'am will take chemistry, and Lakshay sir will be taking biology. All right. So physics we will be meeting every Monday, Wednesday, Friday between 5:15 to 6:15 p.m. right? And the target of this particular course is your midterm syllabus coverage. So the first 5 units of your term 1 syllabus will be covered. Okay. In case if you have missed the previous classes, you can actually watch the class recordings, and the class recordings will be given, right? You can watch the class recordings and you can come to the course, and actually you can during the doubt classes, if you have any doubts, you can solve your doubts as well. The reason why we starting this courses early is that you have going forward in the year, because you're in class 12, you will have more time for revision. All right, and for class 11 also, in case if any of you in class 11 and interested, for class 11 we started a course from 8th June only. It recently started, right? Again, if you're taking class 11 subscription, class 12 subscription is absolutely free. And we are introducing the community feature. So using the community, my community link is also given here, and also in the description box you can actually check out the community link, and you will never miss any update from your favorite educators. You can follow any of your favorite educators community, and you can share feedback directly with educators via pool feature as well. And in case if any of the videos, if you're seeing any inappropriate content, and if you're reporting the same, you can claim a prize. Okay, if you have any questions, I'm happy to stay back and answer. Otherwise, you can, if you like the class video, you can like and share this particular video, right? And you can also subscribe to the channel to stay updated. Again, click on the bell icon so that you'll get notified when the next class is happening, and you will also be knowing about the upcoming classes as well. Okay, and on the YouTube channel, on the Unacademy YouTube channel, right, whatever classes are happening, those details are again given. Right, at the same time, you can follow me on my Telegram channel. The Telegram channel link is also given in the description box. There also all the updates will be given. All right. Thank you for taking the class.